This video is Chem27BBlake. And last year was the first year I had this software, and this time of year I was just scrambling to keep up. So there was a lot of things in this flip charts that were kind of rough. And so I was struggling a little bit here in the last video trying to kind of touch base. And yes, we did talk about electronegativity and polarity of bonds, because all the way back in chapter, I think it was 6 weeks ago, we looked at this periodic table of electronegativities from page 194. And I wrote a note when I put that in the book this year that, hey, there's a very similar one way back on page 265 in chapter 8, which is where we are now. And we were talking about, back then, that if you went to page 266, table 7 and figure 21, you'd see how electronegativity difference is calculated. You find two electronegativities from this table, and then you subtract them. Okay, and then there's table 7. As I said, use table 7 and use figure 21, which is probably, where'd it go? Somehow it didn't get in there. Let's see, page 265. This one. This periodic table of electronegativity, so I need to get that in the notes. In here. So, but we could use the other one for right now. So this is page 4. Let me write myself a note, 265. All right, so I'll put that other one in there. I'll put this one in the flip charts, but for today, I guess you could refer to this one. Now, I usually will know, the basic ones, carbon, nitrogen, oxygen, hydrogen. So to look one up, that's where we'll refer. So this tells you if the difference is less than 0.4, it's going to be pretty much nonpolar covalent. If it's going to be about 0.4 to, okay, I disagree with this table, because covalent means shared. I want to mention this too, because this is in the organic chemistry book, and it's true, that the cutoff between nonpolar covalent and polar covalent is arbitrary. I have seen books and used books where it was 0.3. This book is 0.4. I think the organic chemistry book is 0.5. So let me make a cutoff here. I disagree with how they have this. This should be nonpolar covalent. This should be mostly nonpolar covalent. It shouldn't be mostly covalent, it should be mostly nonpolar covalent. If it's more than 0.4 up to 1.7, it's polar covalent. And if it's 1.7 or greater, this is ionic. And this whole thing are predictions. And you could predict that a compound is ionic. Well, HF, for example, hydrogen fluoride. Fluorine is 4.0. Hydrogen is 2.1. The difference between those is 1.9, so it should fall under ionic. However, it really does make a molecule that's very polar. So these predictions are pretty good. That, yeah, you can find exceptions to them, certainly, and there's a good explanation for each exception. I'm not going to get into why this is an exception right now, but you can find one. Okay. Let's go onward. So we were talking about, and there I included this schematic here. I got that one in there. I also included from page 263, table 6. So I started off in the last video, we talked about tetrahedral for methane, which is carbon, CH4. Ammonia is NH3, it's trigonal pyramidal. The next one we're going to do is water, which is bent. That's the molecular geometry or shape. I was also throwing around the term molecular geometry and molecular shape without realizing I had told you they mean exactly the same thing. This book uses molecular shapes. Most books use molecular geometry. So when you see that sometime in the future, that's what you already have talked about. Okay, so CH4, methane was tetrahedral. The molecule ends up polar because these all end up canceling. Here's that subtraction I was talking about. If it's 0.4, it's on the bubble. Each bond here was above 0.4, so each bond was polar, but these added together to give you an overall molecular geometry or an overall molecular polarity. Now, molecular polarity matters because if this methane has really no polarity to it, and another methane's floating by and has no polarity, there's no positive and negative ends, so they'll just bounce off each other and go on about their merry way. They don't stick very much. So their boiling points would be very low because there's no attraction to stick them together. And I mean very low. Now, ammonia has a much higher boiling point than methane. It's still very low because this is a small molecule, but it has a positive end and a negative end, and if this end's positive and this end's negative and another ammonia comes by, it'll be like, oh, opposites, let's attract. So it'll stick together. So you'd have to add a little more molecular motion at a higher temperature to drive these apart. So the boiling points are higher when the molecule is polar, especially for their size. The next one I want to look at is water, good old H2O. In our example here, it ends up being bent. Why is this the case? Well, valence shell electron pair repulsion will explain it. VSPPR. Now, if this was my water molecule here, because the atoms in my model kit don't have holes up there, water would be something like this. Hydrogen bonded there, hydrogen bonded here to the carbon, to the oxygen. But I have a lone pair up here and a lone pair up here, and those push these other bonds away by valence shell electron pair repulsion theory. And this is the shape we end up with a lone pair up here that you can't see and a lone pair up here that you can't see. Now, when you do that, that's water's molecular geometry or molecular shape. It's bent. But this bond is polar and this bond is polar, because if you take 3.44 for oxygen from your table and 2.1 for hydrogen, which should be back here, oxygen 3.44, hydrogen 2.20. I have 2.1. Different tables will have a little bit different numbers. I'm just used to 2.1 from an old table. So if you take 2.5, wrong one here, 3.44 and 2.2 subtracted is 1.2, 1.3. So this bond's polar and this bond's polar, but they aren't opposite. They aren't opposite like this one. These would cancel. This does not. Because one has got a dipole this way, one has got a dipole that way. You resolve those vectors like you'd learned to do in physics class, and you end up with a leftover vector. So that molecule is polar. And sometimes students are like, well, how does that cancel? Not well, you just don't have the vector resolution skill yet. You haven't learned it in math class or physics. So if you've got a question about that, certainly ask. I'll try to do it without doing the math. The math comes next year. Okay, so going down the table. Out of your book, I'll show you this one. We did methane, then NH3, then H2O, and then I think I'm going to jump up here and do this one and this one. I think that's next. AlCl3, which comes out to be trigonal pyramidal. No, trigonal planar. Okay. This group violates the octet rule. It doesn't end up with 8, it ends up with 6. And you were okay with that. You guys did pretty good with Lewis structures. Aluminum has 3 electrons it brings to the table because it's in the boron family, boron group. It ends up with 6 shared electrons, not 8. It violates the octet rule. So once you do that, valence shell electron pair repulsion theory says you're not going to have this in a 90 degree and a 90 degree and then a 180 degree. They're going to spread out. So you have 120, 120, 120. And the electrons in this bond are going to repel the electrons in this bond, are going to repel the electrons in this bond. So they can't, any one side can't get any closer. And they can't come up out of that plane towards this way without getting closer over there. So 120 is as far apart as they can get. That leads to a molecular shape or a molecular geometry of triangular planar. It's a triangle in a plane, like this. It's pretty close. I would have green ones on here for chlorine. I guess that's going to bother me, so I'm going to go ahead and change them. Usually use green dots for halogens. Okay, this isn't really the right one in the middle, but it's giving me a triangular. This molecule is nonpolar, even though that bond's polar, and this is bond polar, and this bond's polar. If you take aluminum and subtract chlorine, it's 3.2 and 1.6. Aluminum, 1.6. Chlorine, 3.16. Let's say 3.2. Now, by the way, chlorine is the bigger number. So the dipoles point towards the chlorine, towards the chlorine, towards the chlorine, leaving the aluminum end partly positive. But because those dipoles are exactly equal and opposite and symmetrical about this central atom within this plane, they cancel. And the molecule is nonpolar as a whole. This should be next is BeCl2. Okay, so we'll go up here and do beryllium chloride. So carbon group followed the octet rule. Going to the left, boron group has 3 valence electrons. Let me show you this way. So carbon is above silicon, has 4. Boron group has 3 and won't do the octet rule. It ends up with 6. So the one we're going to do next is alkaline earth metal group. I'm going to use a beryllium example. It has 2 electrons, and when it shares, it'll end up with only 4. And they'll sp hybridize. They'll be on each side. We discussed sp hybridization back here. This would be like BeCl2 or BeF2. Okay, Chlorine is 3.2, beryllium is 1.6. Each bond is polar. So beryllium ends up with 4 electrons. It's linear. The molecular geometry or the molecular shape is linear. One that way, dipole that way. Even though both bonds are polar, the molecule is nonpolar because those dipoles cancel. Molecule is nonpolar. Okay, let me see where I'm at on time, how many more I have room for. We'll do one more, that's what I figured. Okay, group 1 elements. Hydrogen and alkali metals below it, lithium, sodium, potassium, this family. Right here. It's got hydrogen at the top. Now I wrote in here that these families don't usually covalent bond. Well, hydrogen does. Hydrogen covalent bonds all the time. Most of the rest of them do not. Most of the rest of them ionically bond most of the time. However, they can covalently bond. And when they do, they violate the octet rule also. They don't end up with 8, they end up with 2. So an example of this would be lithium bonded to hydrogen covalently. You get lithium hydride. And these would be linear, and they're not all that particularly interesting in this chapter, at least, to talk about. Okay, one more. I'll end right there and pick up with another video.